Hello and welcome to our presentation on designing actuation systems for animatronic figures via globally optimal discrete search. This paper is presented by me, Simon Huber, and I worked on it in collaboration with Poranne and Stelian Coros. When we talk about animatronics, the first things that pops to mind are the lifelike animated characters from movies and theme parks. Here we see a collection of a few animatronic figures. We have Abraham Lincoln from Disneyland on the left, Karen from the movie Clash of Titans, and Captain from the movie Hitchhiker's Guide to the Galaxy, both in the middle, made by Biomimic Studios. And on the right we see Mesmer, made by Engineered Arts. Animatronic figures are electromechanical systems that are meticulously engineered to generate lifelike motions. These robotic characters can be made to convincingly resemble a vast array of creatures, real or imagined. Needless to say that the process of designing such models is extremely time-consuming and demands a great deal of experience. Here is one recent and well-known example, the Na'vi shaman made by Disney. It's hard to grasp how many things have to be considered when designing such an intricate machinery. Many things, like range of motion, collisions, spatial constraints, as well as software development and computation time. This is the main reason why ambitious projects, such as the ones I mentioned, could only be done by large studios. However, with the rise of the makers movement and the fourth industrial revolution, 3D printing has become much more accessible. Sharing ideas and designs through social media leads to many designs coming from single hobbyists and tinkerers. Here, we see a collection of designs created by aforementioned hobbyists. Let's look at two of these animatronics more closely. These latex faces appear very real and very complicated, but they are just a cover. Once you tear them away, you can see their true nature. Under the cover, we have a mechanism. An animatronic mechanism has two types of elements, followers and drivers. Drivers are essentially motors, which are attached by tie rods to followers. Followers make up the moving features of the animatronic. We also have force transmission elements. Those can be used to change the direction of force applied by the motor. Let's have a bit of a closer look, shall we? Given a mechanism that already allows all the followers to move in a desirable way, one of the big questions that still remains is how to attach drivers to followers. As I mentioned, drivers are connected to followers by tie rods, but the question is, which driver should be connected to which follower? Or in other words, how do we pair up drivers and followers in an optimal way? This is exactly the question we're set to answer, and in the next few slides I will show you why it is so complicated and how we approach it. Let's start by clearly stating the problem. Our input is an articulated figure with a predefined range of motion for each follower as seen here in the animation. Additionally, we input a range of possible motor placements. The required output is an optimal assignment of motors to followers that enables the specified range of motion. So why is this problem challenging? First, feasibility. Not every driver assigned to a specific follower can provide the specified range of motion. This is a question of torque limits. Next, we must avoid singular configuration. A singularity is the point where the direction of force changes and the force is applied to a follower is zero. Third, we must avoid collisions. All collisions between pairs of tie rods or tie rod and the body of a mechanism are prohibited. Here is a simple overview of our system. First, the user needs to specify the range of motion for each follower. Next, we run the algorithm that computes the optimal driver to follower assignment. Once the algorithm finds a solution, the user can define any motion within the specified range of motion to generate lifelike behavior. To illustrate the assignment process, we begin with a simple example. Here, we see multiple assignments to followers and the trajectory outline. The first thing we need is a way to organize all the assignments. Then, we need to decide whether an assignment is any good or not. For that, we attach a cost to each assignment. Let's first talk about the assignments themselves. We distinguish between a complete assignment, where every follower is assigned to a driver, and a partial assignment, where not all followers have yet a driver assigned. We can organize all partial and complete assignments in a tree, where leaves are complete assignments and all other nodes are partial assignments. The root node is the empty assignment, where no follower is assigned to any driver. In the second layer of the tree, we have one node for each assignment of driver to follower 1. So for every driver not yet used, we create a new node where it is assigned to follower 1. In the third layer, we assign driver to follower 2. For each node in the second layer, we create several children. Each child has the same partial assignment as the parent, with an additional driver assigned to follower 2. For more followers, we just add more levels to the tree until all followers are accounted for. Just to give you some numbers, the number of possible complete assignments, that is, the number of leaves here, is 20. And it is calculated using the factorial formula seen on the left. The number of nodes in the entire tree is 26, and it consists of the sum of the same formula as the one for the final layer, with just always one less for each layer above. These numbers are blowing up extremely fast. Even just for small designs, the number of nodes is immense. A shoulder mechanism with 4 degrees of freedom and 8 motors has around 3000 nodes in the tree. The face with 14 followers and 16 drivers results in a number with 12 zeros. The baby with 24 motors and 10 degrees of freedom has a result in a number with 13 zeros. Back to our tree. We know that the optimal solution has to be in there, because every possible solution is in there. So how do we find this solution? How do we find this optimal path? Since every leaf node is a complete assignment, the question becomes on how to find the best leaf. We cast the problem as a shortest path finding problem. In a nutshell, starting from the root, we search a path to the closest leaf, where closeness will measure the quality of the assignment. What we did is to attach to each node or each partial assignment a local and a global cost. Local costs consider information related to a specific driver-follower pair. The most important property that a local cost has to have is feasibility. With feasibility, we mean that the connection between the motor and the follower is able to trace out the whole trajectory. On the left, we see the motion being followed perfectly. And on the right, we can see in the yellow square that if the follower is constrained to move along the trajectory, that the horn would be torn out of its place on the motor. Assuming that the attachment is feasible, we next wish to evaluate how well it performs. We define the performance measure using the moment arm, sampled over the range of motion. Here you see a follower and a driver and the plane spanned at the hinge joint. Now we project all the points we know of, the attachment point on the motor, the attachment point on the follower, and the hinge point onto the projection plane. But since we need a cost and not a reward, with the projection we compute the inverse of the moment arm, using the formula shown here. This is the absolute value of the dot product between the two projected vectors. Since we get a cost value for every possible follower-motor connection, we can store this in an m times n matrix for each follower and for each motor. When maximizing this dot product, which is basically the inverse of the moment arm, we maximize the moment arm. Through this maximization, we also tell all the connections to stay as far away as possible from singularities. Here, on the left, we can see if we don't maximize for the moment arm, how the blue arrow, resembling the moment arm, changes its direction. So it goes over 0. And on the right, where the moment arm is maximized, how the blue arrow stays close to constant over the whole trajectory. Now that we have seen what properties the local cost has and how it influences the result, we turn our attention to global costs. Global costs are costs that take into account multiple assignments at the same time. As I said in the beginning, one of the major problems when designing actuation systems are collisions. So, since collisions of tie rods can happen essentially anywhere, we need to actively seek them out. To find these specific points of failure, we solve a minimization problem. Then, if the minimal distance is smaller than some threshold epsilon, we add these up to the global costs. And this is a hard problem. To detect possible collisions with the body, like shown here in red, we compromise on a simple ray mesh intersection on a set of sampled positions. Here, a quick comparison that shows the difference between using the local costs only versus using the global costs too. It's a bit subtle, but it can be seen here that with the local costs alone, our algorithm found an assignment that indeed maximizes the moment arm, but also leads to a lot of collisions. Now, on the right, we see that once we factor in the global costs, the solution contains no collisions anymore. So now that we know how to compute local and global costs, we can use this to calculate the cost of an edge on the tree. Underlined in red, we have the local costs of the newly added driver-follower pair, going from a parent node to a child. Underlined in green is the global cost, which is expressed as the sum over all pair of assignments. This completes the formulation of the problem. The problem is now converted into finding the shortest path on a tree, from the root to any leaf. This could be solved using any standard approach, but our particular description clearly calls for using the A-star algorithm. Let me quickly explain. We opted to use A-star of the branch and bound family of algorithms. It's commonly used in path planning algorithm, and it requires two values for a node in a graph. First, it needs a cost that describes the current value at the current node. Secondly, it needs a value that underestimates how far we still are from the optimal solution. In other words, a lower bound on the costs to go. This is known as the heuristics. The tighter the heuristic, the faster the optimal solution can be found. There is a very interesting trade-off between the heuristics. Some heuristics are slower to compute, but provide a tighter bound, which leads to fewer nodes being evaluated. Please see the paper for more details. What values do we use in our tree for these two functions g and h? For g, the current cost, it's clear that we can just sum up the edge costs up until that specific node. For the heuristic cost h, we use the local cost matrix we calculated before. In this matrix, we ignore all the columns and rows of already used followers and motors, and take the minimum values in the rest of the columns. For each follower still to be assigned, 1. This gives us our h. As already noted, we also used other types of heuristics, more accurate ones, and again, please see the papers for more details. Let's see some results. First, let's start with a baby model with 10 degrees of freedom and 24 possible motor positions to choose from. The motors are stacked in 2 overlapping layers, each with 12 motors, to accommodate for multiple motors intersecting. We just don't create a child node in the tree if the parent and child node would intersect with each other. For this result, we created a shoulder mechanism with 4 degrees of freedom and 7 motors and 3 via points. First, again, we defined the trajectory, added some motors, and ran our algorithm. After, we can define any range of motion within the specified range of motions. And finally, the phase. It has 14 degrees of freedom and 16 motors. We also created it physically. When we define the range of motion in simulation, we can directly translate it to the servos in the physical model. In terms of limitations, our method can only find tie-rod body collisions by sampling. Based on the density of the sampling, that would mean there is a risk that some collisions will be overlooked. Another limitation is related to via points, which I didn't discuss so much in this talk. Our algorithm supports via points, but they have to be placed manually. Please see the papers for more detail. In conclusion, we built a tool that advances the traditional CAD software to simulate our animatronic designs. We use this simulation to create an algorithm that calculates optimal assignments of motors to followers. We also support via points, and please, if you want to know more about those, check the paper. We built a physical prototype to validate our design, and lastly, we added a bunch of simulated examples. Thanks a lot for watching.